All right. What can I do for you guys?
I can start.
Great.
In problem set 5,
Okay.
the third question, part 2, we were asked to make the d orbital splitting diagrams for TD and D4H. And we were told that we could look at the character tables, but I understand how we would figure out like what the Mulliken symbols of the character table of the orbitals are. But just given the character table, is there like a shortcut way to think about like the relative energies of them, or would we have to be given that? Like, I know you could like try and really think through the interactions between the orbitals and try and figure it out that way. But is there a shorter way of doing that, or like, yeah.
Sorry, remind me which one. I'm looking at problem set 5. You
Yeah,
said
problem set 5, question 3, part 2.
Part 2. Right.
Like OH and TD, we sort of know, but for something like D4H that I don't know, how, like, is that something I should be able to construct to know that?
Yeah, you should be able to construct it.
Okay.
And so the way that I would analyze it is, I would pick my z-axis, which for cobalt tetraisocyanide like that, that's going to be orthogonal to the plane of the cyanides. And then, I'd look for the strongest bonds in the compound. Okay. And based on like which orbital makes the strongest bond. So for example, the one that all 4 of the isocyanides point at is probably going to have the strongest interaction. And I know it's the sigma bonds that are the strongest bonds. And so, and also if it's a double or a triple bond, it tends to have the strongest bonding interaction in the compound. And that is sort of like one of the 5 orbitals in this case. So which d orbital is that, The
XY.
It's x squared minus y squared. That's the one. You could say xy, but in this class, we've been using x squared minus y squared as the one. And that one is sort of like in the octahedral splitting diagram, it's degenerate with the dz squared, right? So the 2 squared descriptors are the ones that point directly at the ligands, okay? So you got cobalt, CNR, 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 CNR. So there is your z-axis. There's your x and y axes. And so the x squared minus y squared orbital is this guy here pointing right at the cyanides. Right? So that is going to make the strongest interaction. And so if I start with a cobalt that's got 1, 2, 3, 4, 5 orbitals that are not split, and I add these 1, 2, 3, 4 CNR ligands, the x squared minus y squared is going to be split the largest. Right? So sorry, that was a mistake. Let's try that slightly differently. Oh boy. And in fact, I'm gonna just get rid of that. So this guy here is the sigma star level, and this one is the sigma level. Now, let's look at the rest of the orbitals. Are there any other sigma bonds?
Yeah, with Z squared.
Z squared also has one, right? And that's because the isocyanides come off of the donut. Okay, so we can push up the Z squared a little bit too.
Mhm.
Now what's left?
The XY, the YZ, and the XZ.
Yeah, XZ, YZ, and XY. And those things are where?
Between the ligands.
They're between the ligands, right? All right, so they don't make, sorry. Let me stop this thing from going off all night long. Omicron is blowing up in the city, says my brother. So, jeez, I need to, they're gonna get on some tirade here. I need to figure out how to turn off the noise. I'm not sure I even know how to do that on an iPad. Silence. Info. Apparently, I don't know how to do that. All right, well, we may be hearing some noise here. Anyway, maybe I can just turn that volume off. That would be good. There we go. Okay, so there's two of your sigma bonds, right? We've got two sigma stars here. The one that's pointing right at the ligands, then the one that's pointing right at the ligands with the donut. And what is it that's, what is left? What is left? We got XZ, YZ, and XY. They don't make sigma bonds, right?
You're right.
So, shit. I'm sorry, now I've got Siri yelling at me. This is comical. Do I turn you off, Siri? There we go. All right. And so what kind of bonds do they make?
Pi bonds.
Pi bonds for the cyanides. And would you say that XZ, YZ, and XY have different interactions with the cyanides, or are all their interactions all the same?
XZ and YZ are the same, which we also know from the character table.
That's right.
Z is different.
Yeah, XY is different. XY is the one that's between the four ligands, right? So
Yeah.
if you have the four ligands, the XY orbital is the guy that's in between. And that means that it has pi interactions with all four of the cyanides. Whereas XZ and YZ are not like that. Right? They only have pi interactions with two of the ligands.
Mm-hmm.
So there you go. So that tells you that XZ and YZ are going to be lowered less by the pi star orbitals of the cyanides, and XY is going to be lowered more. So let's draw XY down here, which is going to be d pi. And then XZ and YZ is also going to be d pi. So there's your splitting diagram.
And the pi stars, those are higher. Where are the pi stars?
So these are the sigma orbitals here, and up here we've got 1, 2, 3, 4, 5, 6, 7, 8 pi star orbitals on the CNR.
Got it. Okay. That makes sense.
I tend not to think about the ligand orbitals really anymore. I just think about the strength of the interaction of the Ds with the ligands.
Yeah.
And whether or not the ligand is an acceptor or a donor. And if it's an acceptor, then it lowers the energy of electrons in d orbitals. If it's a donor, it raises the energy of electrons in d orbitals.
Yeah. The only reason I ask is to know how to know if something is an antibonding type orbital or a bonding type orbital.
As I say, I think the simplest thing is just, if you imagine there are electrons in that d orbital, okay, forget about MO diagrams, but you've got electrons in a d orbital, and you bring a ligand up to it and you stick it to that d orbital. Are you going to have a repulsive interaction between two electron pairs, or are you going to have a stabilizing interaction between the electron pair on the metal and the empty orbital?
Yeah. Okay.
So if it's a stabilizing interaction because the empty orbital on the ligand is there, then those electrons sitting in that d orbital are going to go down. If it's a repulsive interaction because you bring up an electron pair and a ligand, then those electrons will go up.
Yeah.
Right.
Okay.
And so when I draw these guys out, these levels, if they had 2 electrons in them here, they would go up in energy when you stuff in a ligand into that orbital that already has 2 electrons in it.
Mm-hmm.
Whereas these guys down here, they're going down relative to where they started because the orbital is an acceptor. It's an acid, a source of positive charge, and that stabilizes electrons in those bonds.
Yeah.
If there were lone pairs in the pi symmetry orbitals, like a chloride or something, then you would have any electrons that are in the d orbital that interact with those electrons in the ligand orbital, those would go up. So the pi sigma distinction is not really important. It's just we rarely have a case, we haven't discussed any in the MO context, where the ligand is an acceptor in a sigma sense.
Yeah.
If that were the case, that would pull the energy of the electrons down, even though it's a sigma bond.
Yeah.
Right?
Okay. Thank you. That was really helpful.
Oh, good.
Yeah, I have a question. Can you go back and talk about the steric effects of phosphines?
Sure. Do you have a more specific question than that, or just you want to give a sense of how that works?
Yeah, can you just give me like a general sense of how it works, and then if I still have questions, I'll follow up.
Yeah, I mean, so the example we discussed in class was on a nickel L4, right?
Mhm.
And what we wanted to know is how easily does it lose a ligand? Okay.
Yep.
And the real question is, what's the delta G for this reaction? Is it downhill or not?
It should be downhill if it's happening.
Yeah. Well, it could happen a little tiny bit and be uphill because there's thermal energy in the system, right?
Right.
So, there's the delta G, there's this rule. If let's say delta G equals 1.37 kcals per mole, and let's call it minus, okay? If it's 1.37 kcals per mole downhill, then KEQ equals 10, where this is KEQ. If delta G is equal to minus 2.74 kcals per mole, then KEQ equals 100. If delta G equals minus 4.11 kcals per mole, then
It should
K
be like 10,000, right?
equals 1,000. So these are all just jumps of 1.37 kcals per mole each time. Okay.
Oh.
That unit of energy corresponds to a factor of 10 in probability. This is the same thing as 59 millielectron volts. Those two numbers are good numbers to remember.
Okay.
If you have something that has a barrier height of 59 millielectron volts, the rate constant, or if it goes up by 59 millielectron volts, the rate constant goes down by a factor of 10. Okay, so these are, these are sort of units of factors of 10 in probability world. So what we want to know for this equilibrium constant is it downhill or not? Okay, and the question is, what determines the stabilities of the two sides of the equation, right? What's the stability of the compound on the left versus the pair of molecules on the right? And one of the ways that you determine that is by considering the nickel ligand bond strength, right? This is going to be approximately related to the strength of that bond.
Sure.
There's going to be some rearrangement. There are some entropic things to consider also, but a lot of it is just like bond association energy. Okay. So now if you have a bunch of different ligands, some of them are big, some of them are small, you can get too big. Okay. And like, if L equals tricyclohexylphosphine, you can't make the tetracoordinate compound. If L equals tritert-butylphosphine, you can't make the tricoordinate compound because it's too damn big. Tritert-butylphosphine is a honking phosphine. It's huge, so there's just not enough room. If you were to force that phosphine on there to make a bond, it's going to want to fall apart. It's just too big. Okay, so the size of the molecule impacts the strength of the interaction because you have to get stuff out of the way to make the big ones bind.
Sure.
And that involves flexing the molecule, right? Like if you were actually going to try and pack all those big phosphines around it, you'd have to bend the molecule. And so then it's like all primed to spring open, because when it springs open, it pops and this ligand gets put out into solution. Now the ligand is relaxed again. So it lost a bunch of energy. That contributes to that equilibrium constant.
I see.
Okay. So the strength of the interaction is impacted by the size of the molecule.
Makes sense. So how does that, I remember that you were also discussing the that theta angle.
Yeah, right.
So
yeah.
I'm looking at the data that you gave us, and it seems, well, actually, I can't even say that because so triphenylphosphine, for example, that one had the largest theta angle, but it's not necessarily the biggest molecule.
Well, the theta is a measure of that. Theta, this angle here is a measure of how big the phosphine is.
Okay. Oh, that's right, because of on triphenylphosphine, they're like kind of turned, so they can't.
Yeah, I mean, when they made these things originally, they actually assembled molecular models and just like took a piece of string, and then measured the angle.
Yeah.
Probably there's like conformational issues that also are relevant, right? Like maybe you could kind of spin the substituents and they pack a little bit better. So it's not really an exact science, but the range of angles is huge. The tritubutylphosphine, for example, the theta is more than 180. And I mean, it's really hard to visualize that kind of stuff. But let me just say this, which is a very, very true principle in chemistry over and over again. If you're trying to make a molecule that's bulky, you're going to run into trouble. Bulky things behave differently. Packing of ligands, packing of substituents really strongly impacts reactivity. I've watched two junior professors in recent years from very famous groups at very famous universities start their careers by making bulky ligands. That's what they chose to do. They both were denied tenure, but that's probably not something to laugh about. But their intuition, a chemist's intuition, it tells you, I mean, these are talented people, right? And they expect novel things to happen when stuff is big. And that's because size really matters a lot in chemistry.
I just wanted to, we put like questions in the chat, but I don't know if.
Thank you.
Yes.
Okay. Okay. I want to finish the discussion that Keon started here. Do you have a more specific question about particular numbers in that, or the trend that we discussed?
Well, yeah, because I was looking at the what is it? It's like a para. It's like a toluene with a oxygen. I can't think of the name right
Those
now.
things are called phosphites.
Phosphites. So if I look at that phosphite versus triphenylphosphine, I would have thought that the phosphite would be bigger, but it has a smaller theta angle than triphenylphosphine.
What are they?
The phosphite is 128 and the triphenylphosphine is 145.
Okay. Well, it tells you that the substituent that dictates the size is the hydrogen closest to the phosphorus. That's how I would interpret that.
I see.
And because you add one oxygen and now the phenyl group is further away.
I see.
That's not always going to be true. So for example, like I don't have the numbers in front of me, but tris neopentylphosphine is probably bigger than tris tert-butylphosphine. And yeah, and in substituent effects in organic chemistry, if you're doing an SN2 reaction on a primary alkyl bromide that has a tert-butyl group next to it, that's slow. But if you have a neopentyl group, it's even slower. So neopentyl is pretty big. And that's one methylene group sort of away. So I think your intuition about this phosphite, not, maybe that should be bigger. The issue is the angle is defined by the stuff up close to the phosphorus. I mean, my group, for instance, we work with trioctylphosphine and tributylphosphine and octadecyl chains. And people say, wow, an octadecyl chain is really bulky.
No, see, I wouldn't have thought that an octadecyl because it's so long. It's like only like just like what two hydrogens that are like right there, also with like another carbon.
Exactly. Yeah. I mean, when you're talking about the coordination sphere of the metal, it's the stuff right by the metal. We work with particles, and so you have many of these chains, and it creates this like shell or corona around the particle, and so the sterics are kind of like from the perspective of another particle that's trying to get in there. It's a different reference point. In coordination chemistry, it's like what's right around the metal.
I see. Because I would definitely say that an oxygen is smaller than even like a 2 carbon or like a 3 carbon chain. So I can kind of see that now.
Yeah. Okay.
Cool. Thanks.
You good? All right. Let's see here. Problem set 4. I'm going to go to Ethan's question. Homework set 4. Question number 1. Yes. The following octahedral complexes are expected to exhibit weak, strong, or no Jahn-Teller distortion. Okay, so what causes a Jahn-Teller distortion? Let me just remind you for a second here of this equilibrium that we were talking about. Okay, so if you have a compound that's on the left side of that equation where the ligands are too big, but you just, in your mind's eye, created this substance with 4 ligands around it, but it's tricyclohexylphosphine, and the porous cyclohexyl groups are stretched. The molecule can fix its problem by breaking a bond and allowing everybody to relax into a more favorable geometry, right? That's the thought experiment that we're going to do with Jahn-Teller. In the Jahn-Teller case, you have the same equilibrium sort of picture where all of the ligands are at the same distance. But the molecule says, you know what? I can relax my energy. I can go downhill by rearranging things and making stronger bonds to some of the ligands with my empty orbitals and push away the ligands that are connected to my orbitals that have electrons in them. Okay, so let's just do an example of that for a second. So tungsten, hexamine 2+. We've got 6 electrons for tungsten. You've got 12 electrons for these ammonias. So this is an 18 electron compound. It's tungsten 2+. That leaves you with 4 d electrons. right? So let's write out 1, 2, 3, 4, 5. And we've got 4d electrons here in the diagram in the low spin case. And let's label these guys. So these are the sigma star orbitals. This is dz squared. This is dx squared minus y squared. These guys are non-bonding. This is xy, xz, and yz, right? And they're non-bonding because these are sigma-only ligands. They don't really participate in pi bonding at all. Okay, and so what it means is that the d orbitals down here that make up this EG set, or sorry, T2G set, they don't really impact the energy of the compound. So, you know, you can't really move the ligands around here and have a big influence on what the molecule does, or on the energy of that equilibrium. So let's do the manganese example here, and then I'm going to talk about the answer key, which I think has a mistake on it. Let's do the manganese example. 3 minus. So 3 of those, I'm going to call 3 of those fluorides one of each of those 3 minus charges. And so I can think about the oxidation state quickly as manganese 3. That's also D4. Okay. Now, these are weak field ligands. It's a 3rd row transition metal. And so the splitting is smaller. And that means you're going to go high spin. Okay, so dz squared and dx squared minus y squared are the sigma antibonding levels, and now they have 1 electron in them. Okay, so the molecule is in a position to relax.
Professor, can I ask you a question?
Yeah,
So I don't mean to interrupt you, but the fluorines, those are pi donors, right?
yes,
Okay, so it's not non-bonding, it's a pi star, right?
that's correct. You are correct. Thank you, thank you, thank
Okay.
you. You
Sorry
are
about that.
exactly right. Thank you very much.
Thank you.
So the ligands here are fluorides. They have lone pairs of pi symmetry. And so those d orbitals between the ligands, xz, xy, and yz, they interact with those lone pairs on the fluorides. And that raises the energy of those d orbitals. And that's part of the reason why the gap is small. And that's part of the reason this compound is high spin. So Mac deserves a gold star for that. In this case, right, the molecule can say, look, I've got 2 d orbitals connecting to my fluorides and making the strongest bonds in the compounds. One of them's got an electron. So I'm going to give that to, dz squared and say, all right, dz squared, you hold on to this electrons, you weaken your bonds to your fluorides. X squared minus y squared can get a bigger piece of the pie. And so the molecule will undergo a Jahn-Teller distortion. That's pretty strong because sigma bonds are strong interactions and there's a lot of energy to be gained. And one of the things it might do is contract along X and Y and stretch along Z. Okay, now that stretching along Z is going to split the levels, because compression along x squared minus y squared is going to strengthen the interaction with x squared minus y squared. It's going to make that anti-bonding orbital go up. Stretching the bond along Z squared weakens the interaction with Z squared, and it's going to make that orbital go down. So now you're going to end up with a new arrangement where Z squared is lower, X squared minus Y squared is higher. And what happened? The electron that was in that level went down. Okay, you gained some bonding, you lowered the energy of the electron. Those are changes that stabilize the compound. Now, what about the rest of the ligands or the rest of the d orbitals? This is very similar to the problem we just did with Margot.
It won't be really affected as much. They're not really going to change. They're not going to distort.
So they will distort or they will change in energy, okay, because there are pi interactions. Those changes are going to be smaller because pi interactions are not as strong. The overlap is not as good.
Okay, but can we translate that? Do we translate that like in this octahedral electronic configuration where we're using a Jahn-Teller distortion to lower the energy of the Z squared? Are we going to have to do that with the T2G?
Well, you just did the cobalt tetracyano compound, right? And analyze the orbital energy. So let's do that for this one also, okay? XY, XZ, and YZ are no longer equivalent because this compound is D4H.
Oh, that's right. Oh, yes. Okay, so yeah, it's going to change in that all the things with the Z component are going to be lowered. So YZ and XZ will be lowered in energy as well, and then the XY is going to be raised in energy slightly.
You got it.
Yes. Thank you.
That's right. So let's repeat this. Why did XY and XZ and YZ change in energy? These guys each have one electron. Why are they no longer the same? Because the equatorial manganese fluorines, they're the ones interacting with this XY orbital. There's 4 fluoride lone pairs all interacting with that one XY orbital. It's in between all of those 4 fluorines that are in the square plane. So that XY orbital is now being ganged up on by 4. Right? Whereas the vertical ones, XZ and YZ, they're impacted by these 4, but they're also impacted by these 2. Right? These XZ and YZ levels make pi bonds to all 6 of the fluorines, but the ones that went axial weaken the strength of their pi interaction with XZ and YZ. So now XZ and YZ is not quite as pi star. Did I do this backward? No, I did it right. Yeah, right. These guys are pi star. These are also pi star. This is sigma star and this is sigma star. So when you pull the fluorines away on the vertical axis, the XZ and the YZ orbital, they don't have as strong of an interaction anymore. I really find it hard to draw with these pens. Right? You got these fluorines right here. Here, this distance is kind of long and this distance is short. This distance is long. So, in the Z direction, the pi interaction is different than in this X direction here. The X interaction is stronger. So that's why they split in this way. Now, we had not learned about that when you were assigned this problem set, and it wasn't treated that way when we did the notes. So I think it's, wasn't really drawn out that way in the answer key. But you should be able to know that based on the geometry. You should be able to calculate the energies based on an estimate of what the overlap is like.
So if, like, the interesting thing to me about this is that, like, even though the energies change, the Jahn-Teller distortion changes the energy and the geometry of the molecule, but why is it that they still, like the orbitals, even though they're no longer degenerate, they remain pi star and sigma star? Is that, I don't understand, like, why they don't, does it ever happen with Jahn-Teller distortion that in fact a pi star will turn into a pi?
No,
Okay. And
it's just the strength of the interaction. You know, when you push two things together, you strengthen the splitting. When you pull things apart, you weaken the splitting. And the molecule can rejiggle its parts to get to a more favorable geometry to accommodate the electrons that it has and to accommodate the kinds of bonds that it wants to form.
okay, thank you.
All right, so let's do one more example of this, and then we'll talk about the differences. So chromium hexacyanide, 4-. This is also D4. High spin or low spin?
Low spin?
I like low spin. Why low spin?
Because it's a strong field ligand. Cyanide is.
Because it's a strong field ligand. Carbon is a great donor. It's a strong anionic donor. It's relatively basic. And it has these pi accepting orbitals also. In my lecturer, when he taught this stuff, he always said that the pi orbitals pull it in, and then he'd use his stomach as the lone pair of the ligand to donate to the metal. He'd stand up there and like do this thing in front of the classroom. You know, they worked in concert together, right? And so the cyanide is a strong ligand because it has both that strong carbon, anionic carbon is potent, and it has pi acid character. All right, so low spin. So now you've got 4 electrons down here, and these guys are sigma star. And what are the ones on the bottom going to be labeled?
Pi.
Pi.
Yeah.
Pi, because cyanide is an acceptor. The empty orbital of the cyanide stabilizes any electrons on the metal, right? That makes it pi. So now you can split again. It's going to do the same thing that the other ones did. But this time you're going to have XY on the bottom and XZ and YZ this way. And then the sigma orbitals are going to be the same, x squared minus y squared and XY. Sorry, not XY, Z squared. Right, where these are sigma, sigma, pi, and pi. So we don't get the same splitting this time, right? Now XY is below XZ and YZ. Why is that? Because XY is more stabilized by having cyanides close by in that plane. There are 4 cyanides ganging up on one XY orbital, and those empty orbitals on the cyanides really all work together to help stabilize those poor XY electrons. XZ and YZ doesn't have that same benefit because its axial cyanides kind of stretched away. So they're not quite as well stabilized. So in the case of the hexafluoride, it's the opposite. You know, there it's repulsive. In the case of the cyanide, it's stabilizing. And so that means that you're going to get that opposite ordering. So you have to be able to look at the molecule and say, all right, which d orbitals are pointing at which ligands are what kind of donors and how strong is that? And, you know, in the case of Jahn-Teller, we're stretching and compressing, changing bond lengths for the same ligand type. So you have to consider that. All right, so now
This is a weak Jahn-Teller reaction though, right? This is weak.
yeah,
because-
let's do them all side by side. One quick second, okay? So we've got, whoops, we've got tungsten hexamine 2+, which is looks like this. We've got manganese hexafluoride 3-, which looks like this. And we've got chromium hexacyanide 4 minus, which also looks like that. Let's give these some labels. Sigma star, non-bonding, sigma star, pi star, sigma star, and pi. So when I ask you, is there going to be a Jahn-Teller distortion or not? First question is there an electronic degeneracy? Yes, all of these have an electronic degeneracy. They will all undergo some distortion. Which one is going to be the strongest?
That'll be the manganese hexafluoride or hexafluorine.
Because the one electron, the degeneracy, is in a sigma star level. And if I move the ligands around, that really has a big impact on the energy of a sigma star level. Sigma star levels are very strongly dependent upon, they have very large splittings. So there's a lot more energy to be, recovered by stretching along z squared and contracting along x squared minus y squared. The sigma bonding is the most important bonding in the compound. Okay, so that degeneracy makes this guy the strongest. Sorry, that type of bonding and the degeneracy in it makes the Jahn-Teller distortion greatest in that compound. Now, what about the other two?
Would the weakest be with the tungsten?
Why would you say that?
Well, it's a non-bonding orbital. So I'm thinking that's probably going to be lower in energy than a pi or something with pi symmetry. So if there's any splitting, it's not going to affect the non-bonding orbital as much.
You got it. Good answer. And this one is intermediate. Okay. I would say weak is the right answer. It's really the sigma that matters.
Can I ask a related question on a different problem set?
Sure.
On problem set 5,
Yeah.
question 2, part B, when we're drawing the octahedral one on the right, it's very similar to the manganese hexafluoride complex, but when I was doing it before, I drew it as low spin, and I think that's corroborated on the answer key, but here we have it as high spin.
Part B?
Part B, yeah.
Okay, and we're looking at the
Octahedral.
Octahedral hexachloride.
Yes.
I would say iron 2 octahedral should be high spin, especially with fluoride ligands. So I think this is incorrect.
Okay. That makes sense to me. I just wanted to make sure that was right.
Thank you. Sorry about that.
Thanks.
I also have a question.
Yes.
You might have mentioned this, but in my notes, it says when pi bonding is present, distortions are not as severe. So the one on the left, is it intermediate because the EG is pi, or is it intermediate because there's pi bonding?
It's the chromium hexacyanide is on my screen, it's on the right. I don't know.
Oh, sorry, I meant right. My bad.
The chromium hexacyanide, because the degeneracy is in a pi symmetry orbital, you're going to see, some meaningful distortion. but it's not as significant as moving as a degeneracy in a sigma symmetry orbital. So, and the one on the left, there's basically no bonding interaction with the d orbitals that have degeneracy in them. So even if you stretch and contract and whatever, it's going to have very little impact, or basically no impact, on the energy of those d orbitals. So, you know, it will distort a little bit, but it's hardly going to distort at all.
Okay, so the difference is mainly that it's the one in the middle is high spin, and then there's an electron in the sigma star.
That's correct.
But so what did you mean in class when you said that when pi bonding is present, distortions are not as severe as
Not as severe as sigma,
okay, I see.
just like the example here shows.
Okay, I see. Okay, got it.
Yeah.
Thank you.
Pi bonding doesn't fix the distortion thing or something. That's what it sounded like you hadn't heard from me. You know, it's just where the degeneracy lies. What kind of an orbital is it? Okay, Abdullah is wondering if you give us a refresher on low spin and high spin. All right, so we have three nice examples here. Let's talk about the features that dictate it. Number one, the most important thing to remember is what kind of a ligand is a strong field ligand, and what kind of a ligand is a weak field ligand. And that's all about, in an octahedral complex, that spacing is really all about the character of the orbitals involved. So I'm going to just adjust this slightly to help me make my point. Okay, so on the basis of the d orbital splittings right here, you can tell me which kinds of ligands are implied as being strong and weak field. Okay, a strong field ligand is something that's a really good sigma donor and also a pi acceptor. A cyanide is a classic example of that. It's a good, strong sigma donor, and it's a decent pi acceptor. And that leads to a large splitting in this EG and T2G level, right? The sigma star level that you got up here is way up high in energy because those cyanides are potent donors and they make strong sigma connections. And then at the same time, the pi symmetry thing, it kicks in and helps to lower those other levels, right? Like I said, the cyanide works together. You know, the pi star stabilizes the electrons that are in those pi levels, and it really gets in there and pushes up the empty orbitals. Okay, so that gives you that large splitting. So that is the definition of a strong field ligand. Okay, so let me finish my story here, and then we'll answer. We'll have a chance for comment. Okay, so this one here. Here's another case, but notice that delta O is a lot smaller. And it's a lot smaller because of pi effects. Right? Now it's pi star. So when you push the ligand onto the metal, you got the lone pair pushing toward the sigma orbital, and you got the lone pair pushing toward the pi orbital. And those both push the orbitals up. Whereas cyanide, one gets dropped and the other goes up. So pushing cyanide splits them more like this. Pushing fluoride splits them like this, or like pushes them together. Okay, and that gives you a smaller delta O. So you look at the molecule that you're considering and you ask, you know, is this a potent donor? An example of a potent donor is a methyl anion. Woo, that's a potent donor. Methyl anion, that stuff's dangerous. You know, it's such a potent donor. Water stinks. It's wimpy. Phosphine, pretty good donor. Ammonia, pretty good donor, but not, you know, not a super duper donor. Now you get over to stuff like fluoride. Not only is it sort of like a so-so donor, not really a great donor. It's also got these pi effects. And the pi effects act to shrink that splitting. So halides like fluoride, chloride, bromide, those are all weak field. And then you got special cases like CO and cyanide. These are special because they have both sigma and pi. They're good sigma donors and they're great pi acceptors. And they make kind of a multiple bond. You know, when the cyanide and the CO and an isocyanide, those things bind to a metal, you get two connections. There's this and the lone pair going together. You know, and then you can write these resonance structures where you push electrons from the metal to the ligand. Now you got metal carbon double, or even we talked about triple bonds, you know, with really electron rich metals, you can make a metal carbon triple bond out of a CO and a carbon oxygen single bond with some negative charge out there on that oxygen. That's a really strong interaction. So when you have sigma donation and pi accepting going together at the same time, that really gives rise to large ligand fields. And it's a consequence of the orbital symmetry. Okay. You want to chime in here, Abdullah? Do you want to?
Thank you so much. I was just kind of like to summarize. It's like all of this is just based on the parentage of the orbitals with like the fact, like for example, with the diagram on the right with the pi acceptor, we have a larger gap because the cyanide is at a higher energy level. So then the metals orbitals get pulled down. And
Yeah,
like it's all
yeah.
it's all a result of the parentage of the orbitals.
Right, correct. And I, you know, I hear you saying what you said, and I know a lot of people think about it this way. You know, the cyanide pi star is higher in energy, so that when it makes into connection with the metal, it goes down. That's fine. That to me feels like rote memorization. That's not how I think about it. I think about the cyanide and the CO as having a positive character in the orbital of pi symmetry. And so any electron that's on the metal, because all of these splitting diagrams, what we're drawing, we're talking about them like they're the d orbitals on the metal. And the ligands are just these like things that are modifying the d orbital energies. And so when you have an empty pi star orbital, then you bring that up to the metal, any electron that's interacting with that on the metal, that electron will drop because a source of positive charge makes it harder to rip that electron out. We're measuring the energy of the electrons relative to pulling them off the molecule and putting them in vacuum. When you bring up something that's positively charged, it helps to drop them down in energy. When you bring up something with negative charge, it pushes them up in energy. So a cyanide and a CO, they bring up a pi star orbital that is a source of positive charge that helps those electrons to delocalize into the ligand, experience some, you know, some stability, and they bond to the molecule more effectively, and it makes them harder to pull off. An energy level space, that means it's going down. Okay, if I had a random electron in a vacuum and a random proton in a vacuum, and I brought them close to each other, the energy of the electron relative to where it was with no proton is going to go way down.
Thank you so much. That really clarifies things.
Good. Yeah, that's, you know, that's how that's how I look at all these problems. I just remember where the orbitals are, their shape, and whether it's a, you know, plus plus or plus minus or minus minus kind of interaction. It's acid-base chemistry. Or, I mean, I don't know, maybe it's just electrostatics. It's not really acid-base chemistry, it's electrostatics. That's not the only way to think about it, but that's the simplest. Okay. Oh, so somebody's asking about the frost circle. The frost circle, you draw a circle. Whoops, that's not the circle I'm looking for. Let's draw a circle. And let's pick a ring. What ring size do you want to do? 4? Let's do 4. If you have a ring that has 4 carbons in it, let's draw the point down. Okay, start by drawing the point down. So you got a point here, a point here, and a point here. And each one of those points, this is now a ring of a square ring of p orbitals gives you a level here, a level there, and a level there, and a level there. So these are the wave functions for a cyclobutadiene ring that has 4 equivalent bond lengths. And there are 4 electrons in it. That's the molecular orbital structure for cyclobutadiene. It's a triplet. But cyclobutadiene is not a triplet, actually. Because what it does is it changes shape. It does something that is analogous to a Jahn-Teller distortion. It's very similar to a Jahn-Teller distortion. It's called a Perier's distortion. And now you have 2 double bonds and 2 single bonds. And that
Can
splits.
can I ask a question about this thing that we're doing? So we have the wave functions, the size,
Yeah.
right? And so these are the freestanding waves of each one of these orbitals that are for the entire molecular orbital. This is the constructive interaction between 3 different orbitals in this molecule that are actually creating a larger single wave function for this molecule. Yeah, this is.
On the bottom, we have 0 nodes. The next one, we have 1. Whoa, undo, damn it. The bottom, we have 0 nodes. Then we have 1 node, and there's 2 orientations of that 1 node. And at the top, we have 2 nodes. That's how you make the MOs for an aromatic system. And of course, butadiene doesn't have 4 equivalent bonds because it doesn't want to be a triplet. It's better for it to just rearrange like this and do this thing called a Perier's distortion. Let's do another one. Let's do cyclopentadienide. Draw the point down. Right? That's a square. Here's a 5-membered ring. So you got 1, 2, 3, 4, 5. That's the molecular orbital structure for cyclopentadienide. Or it could be cyclopentadiene, just 5 electrons instead. But if it has 5 equivalent bonds, then it'll have this overlap. And that's splitting. In the bottom, they're all the same. And then you add a node. And then you do it again with a different orientation. And on the top, you have 2 nodes. I don't know if I got those exactly right. There you go. Okay, so the frost circle, you just draw the point down. And, for aromatic 4n plus 2 electron systems, everything looks hunky-dory. Okay?
Okay, thank you. but I guess like I get to this point. So this for an aromatic compound, and we can find out the amount of nodes that are in each orbital, right? Or I'm just confused. Like these nodes exist in the molecule itself, but we're showing it like one energy, there's no nodes. Then we go up another wave function.
Remember the rope trick where like in physics class or Gen Chem, two people stand and they wiggle the rope around?
Yes, the
And
freestanding
you
wave.
wiggle it harder and you get more nodes.
Ah,
Same thing. These are the way that you make a standing wave out of p orbital functions,
okay.
just like the standing wave in a rope in physics class. These are the standing waves that you make out of p orbital functions, 0, 1, 2. You can keep going. You know, you got six rings or six p orbitals in a ring. You can have a 3-node one.
Okay, and do the nodes change like the energy? Does the energy raise as the nodes go up?
Yes,
Okay,
just like in the rope.
thank you so much. I appreciate it.
Yeah.
I'm sure everybody already know. I just
No,
Thank you.
Mac, that's not how it works. Everybody's learning this stuff, and even if they kind of know it, it's helpful. So it's good that you ask. I mean, it's better that we have questions and get somewhere than not. Let me, William, finish the last thing Mac wants to ask about. Okay, this thing down here with 0 nodes is unipolar. This is dipolar, and this is quadrupolar. Now I'm just looking at the top half, okay? So I'm ignoring the fact that there's a node in the plane of the ring when I say that, but if you had just s orbitals in a 5-membered ring like this, these definitions would be right. It's interesting, you know, if there's a mass spec technique called quadrupole mass spec, okay? And what they do is it's got 4 magnets in it. They're rings or tubes. And what they do is they make 2 of them plus across from each other and 2 that are minus across from each other. And that creates a quadrupolar field. It looks just like a d orbital, right? Down the length of this thing, ions get shot into it and they're stuck between 2 positives here and 2 negatives here. And then what they do is they alternate the current. So they switch where this guy's plus, these 2 are plus and these 2 are minus, and then it becomes these 2 are plus and these 2 are minus. And they do that really fast. And the charge gets caught in the middle. It's the only place where it can go without experiencing an increase in energy. And so it leads to this focusing of ions down this column. That's where the term quadrupolar comes from in mass spectroscopy. I'm sure that I butchered.
That is rad. That's
It is
can I just
really
say, like,
cool.
I don't know, that's rad. That's so
Yeah,
cool.
I mean, I probably butchered the description of that, but that's basically how it works. And you know, so that quadrupole, a d orbital is a quadrupolar function. Okay, so when you have an optical transition, you can have a dipolar transition. You can have a quadrupolar transition. A dipolar transition is when charges move in one direction from left to right. You know, in these MOs that you see here, there's a nodal plane. There's plus on one side and minus on the other. That's dipole in a way, right? There's no charge difference between them. It's just the phase of the orbital, but it has the shape of a dipole. Because on one side it's plus, on the other side it's minus. A quadrupole, like a d orbital shape, that's these guys here, right? That looks like a d orbital. So
Oh my God, okay, yes.
when you do a quadrupolar, when you do a transition that has a quadrupolar moment, the charges move in that fashion. And the motion of charge in that fashion leads to an excitation process people call a second order absorption or nonlinear, where linear is the dipolar one. This is a nonlinear transition because it has higher order moments, quadrupolar moments. Infrared absorption, optical absorption, those like collisions of an electric field oscillating in a photon with an electron, those are dipolar excitations. They're linear absorptions. It's a standard absorption experiment. They're intense. Quadrupolar transitions, Raman spectroscopy, plasmonic transitions, all kinds of stuff. Some frequency, second harmonic generation, those types of things involve quadrupolar transitions, and the strength of them is usually related to the polarizability of the fragment. Okay?
Yes.
So when you're looking for, is this Raman allowed? Is this infrared allowed? You're asking whether or not the motion in the vibration leads to a charge distribution that's dipolar in character.
Thank you so much, Professor. I appreciate that. Thank you
Yeah,
for
yeah.
explaining.
All right, William?
It's actually in relation to this for the first bit. Can we talk about assigning Mulliken labels to the sounds we derive from these models?
These guys here in the, sure. So this guy is D6H. Okay. And so, the Z-axis is kind of up and down through that ring. That's the principal axis. That's the C6, right? So if I go down here to the bottom and I say, does this thing, first of all, it's singly degenerate, right? And so therefore it's either going to be an A or a B. If I apply my principal rotation, does the wave function change sign? The answer is no, because it's plus everywhere, right? So this is going to be an A. And then after that, it's going to be some plane of reflection. And I think because of I think this is probably A1. Or I guess maybe it's A1U. Because we're talking p orbitals now, above and below the plane. So if we're talking p orbitals above and below the plane, it's anti-symmetric with respect to inversion. Now this thing actually, sorry, this is not D6, this is D5. I got that all screwed up. I was doing benzene for a second there. So now there's no more inversion center. So it's just going to be A1. Okay. All right. So let's look at the next two. Well, the next two are both E's, right? And, then it's just a question of whether the orbital is symmetric or anti-symmetric with respect to the operation of the next level of importance. And I'm guessing this one is going to be like E prime, and this one's probably E double prime. So let's do the cyclobutadiene. This time, let's do it in D4H and let's do p orbitals again. Okay, so we're only looking at the top half of the lobes right now. So principal axis of rotation is here. You got a C4, right? And singly degenerate on the bottom. So that's going to be an A. Well, I'll use lowercase. It's going to be an A. Plane of symmetry is going to be A1 because it's symmetric with respect to reflection left and right, no matter which plane you choose, except for the sigma H. That's where it starts to get plus goes to minus. This one in the square form has a center of inversion. Okay, and so this orbital, when you go plus on top right to bottom on lower left, it changes sign. So this is going to be A1U. Right? Because the inversion center, if it goes from plus to minus, that's an anti-symmetric function. And that's a U. All right, so this one here is an E. And I would guess that this is probably E2U, no, E2G. G. Because these are symmetric with respect to inversion, right? Minus on top right becomes plus on bottom left. No. Yeah, sorry, minus on top right becomes minus on bottom left. So that's a G. And it's a 2 because a plane of reflection where the node is gives you a -1. So I would guess that's E2G. And then the top one, singly degenerate, you apply a C4 operation and it goes from plus to minus. So that's a B. It's a U because top right plus goes to bottom left minus. So that's anti-symmetric. So that's a U. And then plane of reflection looks like it's a 1. So I'm giving it a B1U.
Thanks. I just wanted to double check that on. I was trying
You
to-
are just testing me. That's what
I was going through the frost circles on my own and I wanted to double check it as it was happening. I'm very sorry. And the second half was, I have the trend for your kinetic assessment of hydricity, and I'm kind of struggling to remember what the general pattern as we were going down was. Could we rediscuss that, please?
Sure, yeah. I don't have the example in my mind. I can go look for it. But let me just tell it to you this way. Hydricity is a measure of how ferocious the compound is.
Okay.
Like giving up hydride. Hydricity tells you about the energy of delivering hydride, right? We talked about that delta G in the equilibrium binding of ligand to nickel and the energy of relaxation when you undergo Jahn-Teller distortion. Hydricity is an energy, I may get the definition wrong. Jack would probably love to correct me here, but hydricity, I believe, is a measurement of the energy of hydride transfer. Okay, and it's sort of a measure of how electron-rich hydride starting material is. So a compound that really wants to give up its hydride is probably an electropositive metal with extremely strong electron-rich ligands around it. You know, so like a zirconium bis CP star zirconium dihydride. Woo, that's a whopper. That's like if somebody gave you water and magnesium hydride and said which one is more hydritic, you better be guessing magnesium hydride. Right? The bis CP star zirconium dihydride is like magnesium hydride.
So that would also mean that the addition of ligands that can participate in high back bonding, drawing electron density away, increases your kinetic.
Yeah, because
kinetics,
you know when you deliver. So if you've got a metal hydride here and some other ligand, okay. Now you're doing this reaction. The equilibrium constant there is the hydricity.
Okay.
Okay. Or the delta G. So hydricity is proportional to the delta G minus. And so, you know, basically, how easy does the H minus come off? Well, if you wanted to measure this equilibrium constant, you should be asking yourself, if I want to make a really hydritic hydride, how do I stabilize the thing on the right? I want it to go to products because I want to give that hydride up, you know, to my reluctant substrate. So I need a whopper of a hydride donor. One of the ways you can assess that is by, you know, how do I stabilize this positive charge here? Right? Because you're making a positive charge to give up that H minus. So if your ligand is really good at donating electrons, it's a really strong donor, that helps to stabilize that positive charge. You know, the metal says, you know, I'm working with an amido substituent over here. I've got plenty of electron density. I'll give up the hydride, no problem. But if it's got some electron deficient thing stuck to it that's needy and taking away its electron density, then it doesn't want to give up the hydride. So the hydricity is a measure of the electron density around that metal center and how the electropositivity of that metal center.
And that follows for the phosphines also, like if we had a halide phosphine versus a benzyl phosphine.
Yeah. Or how about, let's consider these ones here. Which one would you rather be quenching?
One on the right.
Let me tell you, aluminum hydride reagents cause fires, people. If you're ever quenching one, you better be careful and you better know what you're doing and you better be prepared for a fire. It's the most common cause of fire in a chemistry lab.
So when you're like talking about like having something that's able to put electrons on the metal, so it's more hydridic, it's willing to let go its electron or let go of an electron, it's willing to be oxidized. You want a more electropositive metal, meaning a metal that is more willing to let go its electrons. And if you had something like a porphyrin ring or a macrocycle that's sitting around your metal, that's a very electron rich like ligand, and it's able to donate a lot of electron density to your metal, so you have a more hydridic metal at that point.
Correct.
Awesome.
And in these three examples here that we're looking at, aluminum tetrahydride anion, those three other hydrides give up a lot of electron density. The alkoxide ligands around this aluminum, they're electronegative substituents. So that helps to sort of temper the reactivity of this hydride. So this one here is called selectride for a reason. It's selective because it doesn't just indiscriminately reduce anything that gets in its way. And it's because of the electron withdrawing nature of those alkoxides. They're electronegative and that kind of cools it off a little bit.
Thanks, Sean.
All right. Jordan wanted me to do one. Jordan says, could you go over dissociation of MNO to get MN for each resonance structure? All right, let's do some NO resonance structures. No notes. Oops. All right, so first of all, I'm going to just start with a metal like this. I'm going to give it one more electron. And I'm going to call this MN. And now I'm going to add this to it. There's my NO. So let's make a connection. Okay, so when you bind NO in this fashion, you oxidize the metal by 1 because the NO ligand is acting as an X-type ligand. Now, we know things can get funky from here. So let's draw this isomerization reaction. Look at what we did there. In this case, we took these two single electrons and we made a connection. In this case, we pushed those electrons toward the nitrogen and we pushed those electrons toward the metal. And now you have two electrons over here and only two electrons instead of four. You have a new bond also. Okay, so you push the two electrons off the oxygen toward the metal. Now, this is one of several possible resonance structures. Oh, what happens to the oxidation state?
When you donate 2 electrons, it doesn't change.
We just did electron transfer. The ligand actually got oxidized twice. One from, you could think about it as one electron from the nitrogen, one electron from the oxygen going to the metal, and the two remaining single electrons that were part of lone pairs make a bond. That would be a way to do that math if you wanted to account for them. Or you could say the electron pair comes off the nitrogen and it's replaced by this electron pair from the oxygen in the formation of a triple bond. But in any case, you're transferring 2 electrons. So this is N-1. Remember, bent NO donates how many? 1 electron. Linear NO donates 3 electrons. Your cat's really enjoying this.
Yeah, she loves these Zoom meetings.
She's big into electron pushing, I see.
Yeah.
All right. So let's draw some more resonance structures for this thing, okay? My wacky looking charges and electrons all over the place. N-1. Now, notice I'm using a double-headed arrow here instead of a pair of arrows because this is no longer an isomerization. This is a resonance structure depiction. So let's push some electrons toward that nitrogen. Well, let's do it again. So there's 3 resonance structures for the metal. And I like this one over here on the right the most. This is like nitrido N oxide. And that's good. This is like NO plus L type ligand. That's not so good. NO plus L type ligand stinks because it's electron deficient, not electron rich. L type ligands don't really bind, or L type ligands bind as donors. And that's a really wimpy donor. It's a very good acceptor. And as it accepts electrons, it heads over toward this nitrido N oxide form. All right, so Jordan wants me to, she said, dissociation of the metal NO to get the oxidation state. All right, so we have this N-1 here. And when we push 2 electrons onto the ligand, and push two more out toward the oxygen. We're going to do the inverse of what we did on the top. Each one of those motions involves a change in oxidation state of 2. So this is n plus 1. And we're going to do that again. This is n plus 3. Let's, instead of just knowing that when we push 2 electrons from the metal onto the ligand, the oxidation state goes up by 2, right? Because the ligand owns the electrons in oxidation state land. So when you use the electrons from the metal to make a covalent bond with the ligand, which we've done in these resonance structures, you're losing them to the ligand. So the oxidation state is going to go positive by 2 whenever you do that, okay? And that's what's drawn here. Let's talk about this structure on the right and use the, let's count the number of X-type interactions, is it maybe a way to say it? So, you know, what I see, how do we do this? How do I talk about it? Well, let's pull this thing off as n dot dot dot, because we just broke those 3 bonds covalently. Oh, this is minus, and this is plus. Okay, if we wanted to determine the formal charge, we cleave the bonds homolytically. And so if we were to just cover up this guy for a second and look at what's left over, the bond that was being made to that nitrogen center would leave 1 electron behind. That gets you to 4 electrons around the nitrogen. So that's an N plus. Okay, so you can see that there are 3 single electrons being used to make covalent bonds to that metal center. That's like an X3 ligand. Okay, so it's like X3 ligand. Let's do another one. Let's do a metal nitrido. Nobody has a problem saying, well, yeah, that's an X3 ligand. Right? Let's stick some stuff to this nitrogen. How about a proton? Does that change how many covalent bonds the nitrogen is making with the metal? No, proton doesn't do anything to the metal. Let's do another BF3. Neutral thing comes up and sticks to the nitrogen lone pair. That doesn't change the metal. It's still a triple bond to the nitrogen. You know, it's just using its lone pair to make other connections. Right? N oxide is sort of similar. It's sticking to an oxygen atom. That's how N oxides are often drawn. That doesn't change the fact that it's still a triple bond to between the metal and the nitrogen. Let's take a look at this doubly bonded one. That one is harder. So we're going to pull this off as a closed shell fragment. Sorry, this is n+1 because this is a plus here. That's better. So if you pull that thing off as a closed shell fragment, now you have an NO minus and you have a metal plus. So that's a metal n+1. So that's sort of an easy way to do that. But let's do another version of that, okay, where you have actually this one here. That is clearly n+1, right? Because we know NO is just an X-type ligand when it forms a double bond out there and has a lone pair on the nitrogen. And the resonance structure we're talking about is actually this one. That's just an L-type donation, still n+1. You can also write it out in the more formal way. Still n+1. The pair of electrons that gets donated from the ligand to the metal forms a double bond, as drawn in these resonance structures here. But the ligand owns the electrons in the oxidation state formalism. So that donation from the ligand to the metal doesn't change the oxidation state. When you donate from the metal to the ligand, that changes the oxidation state. Because the ligand owns. Any electrons that you depict as part of a bond, the ligand owns. Okay. This little thing right here, you know, this is relevant in a bunch of different cases. Not just NO. Imidos, oxos, alkoxy compounds, you can draw lone pairs donating, halides, lone pairs donating. You draw a resonance structure where there's a formal double bond there. When you do that and you donate 2 electrons from the ligand to the metal, it doesn't change the oxidation state. Okay. Abdullah, these will be posted on the YouTube channel. The exam review is being recorded, so you'll be able to see all this stuff. Anybody else? Well, then I will just take a moment to remind you that COVID is really spiking in the city right now. I'm hearing it from all different directions. I had somebody to my house with COVID on Friday. My brother, he's a teacher in an elementary school downtown. His campuses are having outbreaks left and right. You know, now would be a good time to be a little bit more conservative about getting together indoors with other people, particularly since your exams are coming and probably many of you are traveling and stuff. So if you have a conservative bone in your body, now might be the time to exercise it. I will watch my inbox, and you know, if you guys have questions, I can try and fire off responses between now and Friday. I've got plenty of other things I've got to do, but I want to make sure you guys are as ready as possible. And you know, I'll watch the. Let me repeat what I said a little differently. If you have a question that you would like answered, please put it up on the chat board that we have for the class. Okay, that's a lot more useful for everybody else. No one else?
I do have a question about problem set 6.
Okay.
The very last question where we have I think it's a chlorine. There's like this big macrocyclic compound. I don't have it in front of me, but I think it's question 4 on problem set 6.
Mm-hmm.
And I know we went over like the last few classes we've had, you know, we've gone over some ligand substitution stuff and like, you know, the intermediates and even the stuff that I talked to you about earlier today. And I just wonder if we could just go over that last problem that's on problem set 6, since we
Sure.
didn't have to like turn it in or anything.
Yeah. Yeah, I wish I would have gotten a little bit further this term than we did, but I went slower to try and ensure people knew what was going on. Let me do a new share real quickly. So just so everybody's looking at the same thing. All right. And Ken, are you looking at my, you see the problem set in front of you here? Yeah, okay. All right, so we've got this equilibrium. And, you know, again, what we're trying to do is to measure the favorability of making the compound on the left or the compound on the right, okay? And, you know, let's see here. In this particular case, what they've done, this is some research paper from days gone by, where the X substituents out here on the ring are easily modified. Easily is maybe not fair to the people who did the work, but you know, you can change X from methoxy to methyl to hydrogen to chlorine. And now you've got to be asking yourself, well, what is that going to do to the character of the metal complex? Okay, so a methoxy substituent on the pair position of an aromatic ring is a pi donor into that aromatic ring. And aromatic rings with methoxy substituents are more easily ionized. They are more electron rich. Yes, the oxygen is electronegative, but the dominant issue here is how the electron pair of that substituent interacts with the pi system of the benzene ring. So a methoxy phenyl is an electron rich thing compared to a toluol, where you have a methyl in that position instead of methoxy. And a methyl in that position instead of a hydrogen, the methyl compound is more electron releasing than the hydrogen compound. And when you put a chlorine out there, the pi donor thing doesn't really matter as much anymore. And now it's really governed by electron withdrawing effects. Okay, and so the equilibrium constant, you can see that it parallels that. The equilibrium constant is largest when you have a methoxy substituent and smallest when you have a chlorine. So let's go back up and look at the equilibrium. What's happened? We went from a neutral compound to a cationic compound with 2 imidazoles. And that is easier when the substituents are electron donor substituents, methoxy groups, or methyls. Okay, and so that tells you that the compound on the right is kind of like hurting for electron density around the iron. And that substitution reaction where the 2 imidazoles come in and pop off the 1 chlorine is easier to do when the porphyrin has electron-rich substituents on it. And that makes that equilibrium shift over to the right. Okay, now, there's not really a lot of change here. You know, you got a factor of 7. That's nothing. In chemistry, factor of 7 ain't squat. You know, a real trend is like 10 to the 6. So this is a small perturbation, but it's a meaningful one, right? Like I was telling you before, a factor of 10 in an equilibrium constant is equal to 1.37 kcals per mole. This is a factor of 7. So whatever, that's about 1 kcal per mole difference between the stabilities of the energy of this equilibrium as you change the substituent. So that's not a whole lot. All right, let's see here. So that's the origin of the change in the equilibrium constant. I think there used to be, we've given this problem before actually, and I think it used to have UV vis stuff in it. But anyway, so that's, that's how I would explain the substituent effect on the equilibrium constant. Over and over again in this class, in the latter parts of this class, we are analyzing how electron-rich ligands are and the effect that electron-rich ligands have on reactivity. And it's largely about stabilizing charge. When you have a metal center that kind of gets electron deficient, it becomes easier to form it if the ligands surrounding that metal are really good electron donors. Doesn't mind becoming cationic if it's got all these potent electron donors around it. The cost of making that electron deficient intermediate isn't so great anymore. And that means the energy is lower. That means the reaction is faster or the equilibrium is further to the right. Or maybe we're talking about hydricity, right? More electron donating ligands makes hydrides more electron rich and more hydritic. Or maybe we're talking about CO vibrational frequency. The vibrational frequency of a CO is related to how electron rich the metal is. People use CO as like a thermometer. They stick it to the metal and they measure the frequency and they compare it to other compounds that are like that. And they say, wow, our compound's very electron rich because that frequency is really low. So everybody's trying to measure the electron donating power of their ligands because it dictates things like whether that metal is reactive. Does it do hydride transfer? Does it do ligand substitution? Do the ligands fall off easily or not? Do ligands bind to it easily or not? So electron richness is the name of the game in a lot of discussions about the reactivity of transition metal compounds.
That is, it's so cool. And then also, like, if you didn't have it on like the number 4 locant, right, for these benzorines, but if you had it like, you have para and you have ortho, if you change the location, it's not going to have like much effect really, and you just have better electron donation on the 4 position.
Yes.
Okay.
Yeah, so like if you were to measure the pKa of the free porphyrin, no iron, but just how easily you could rip a hydrogen off of one of the NH bonds, the pKa would also trend with that.
Okay.
Substituent.
And like electron donation via resonance is stronger electron donation than like induction, right? If there was like an induced, like
that's too broad
CH3.
brushstrokes of a statement for me.
Okay. Well, okay, so I can't always say that then. I can't always say that just because something is donating electrons via resonance, it's going to be more activating or more hydritic of a molecule than if it had induction, like the CH3 or whatever. For like a CP star, a CP star will do strong sigma donation. And so I don't know if you can stick a CP star on the end, but it also has like these methyls, which are electron rich, that are attached to each of the carbons. And so it can push electron density onto the center of the CP
Yeah, I mean,
star.
exactly. It's the same thing as like T-butyl lithium versus N-butyl lithium. Right? T-butyl lithium, that stuff is potent. N-butyl lithium is not so potent. I mean, it is very potent, but it's not nearly as electron releasing as a terbutyl lithium.
Okay.
It's got all those methyl groups right packed around that carbanion.
Cool. Well, thank you so much for explaining that.
Yeah. We good? All right.
Thank you.
Yes.
Thank you.
Good luck.
Thank you so much for your time.
Of course. Yeah. You guys hang in there. Almost done.
Thank you.
All right. See you, Juan. Good night, Keon.
I also asked in the group chat, I don't know if you noticed, but could we have like a PDF version of like the notes we took today, or?
Yeah, I'm gonna post this recording online.
Perfect. Thank you so much. I really appreciate it.
You're welcome, Abdullah. Good night.
You too.